Okay, so in this video, we're going to have a continuation of part one of the moon problem, where we have an object that has dropped off the side of a cliff on the moon, and we're trying to calculate its terminal velocity, the percent of its terminal velocity when the object hits the ground, and kind of a generalized function that can grant us the velocity of the object given the position of the object at some point in its trajectory downwards. So I've already written some of this stuff out. I'm just going to quickly review it. It's mostly just algebra, but I'll just provide a quick walkthrough. So to begin, this is kind of what we derived in the last video, where we have y equals m over 2k times the natural log of mg minus kv squared plus some integration constant c1. So this integration constant c1 is determined by a boundary condition, namely the velocity of the object was 0 at y equals h, or in other words, the object was dropped from rest. So the way to implement this boundary condition is to just plug in v is equal to 0 at y is equal to h. So we plug in y equals h, we plug in v equals 0, and then we do the algebra to solve for c1. And that is going to be the c1 that we always use for this problem. So that comes out to c1 equals h minus m over 2k times the natural log of mg. Plug this c1 back into the original expression right here. We'll get y equals m over 2k times the natural log of mg minus kv squared plus h minus m over 2k times the natural log of mg. You could do some algebra here, simplify, pull out the m over 2k term, and you'll be granted this relatively simple expression afterwards. Okay, so now that we've done some algebra, we're very close to being able to create our target function v equals v of y, where v is the dependent variable and y is the independent variable, such that if y is given to us, the position of the object is given to us at some point in the object's travel, we can grant or calculate the velocity of the object at that point. So here we're just doing some more algebra, breaking out the natural log right here. So it's isolated on one side, and then we're raising both sides with e. We have this argument here, mg minus kv squared over mg, on the right-hand side as a result of this expression right here. And then, unfortunately, we don't have such a simple distillation on this left-hand side, so we're just left with e to the 2k over m y minus h. All right, so now we're just doing some more algebra as we're going through. We're just trying to isolate kv squared. So we're bringing mg over, and we're solving for kv squared. We've isolated kv squared, we take the square root, and this is our final function. This is our function v equals v of y, the function we've been trying to derive for this problem. So again, if I'm given the position of the object at some point in its travel y, I can plug that in and get my velocity at that point, v. And the only caveat to this equation is, if you'll remember from the first part of the video, this function is only defined for kv squared is less than or equal to mg. And that restriction was required because it was needed to get rid of the absolute value in the natural log function. So this function, again, is only defined for kv squared is less than or equal to mg. Our more physical interpretation of this restriction right here, and an equivalent interpretation, is this function is only valid for velocities that are less than or equal to the terminal velocity. If this function gives us a velocity that is greater than the terminal velocity, we know it's non-physical and we can't use it. However, if this function gives us a velocity that is less than the terminal velocity, we know it is physical and we can use it. So that's great. You calculate a velocity, you compare it to the terminal velocity, you make sure it's not higher than the terminal velocity, and you know it's good. That being said, you need to know what the terminal velocity is to make that comparison. Fortunately, the terminal velocity is not nearly as involved of a process to calculate as this function was. So if you'll remember what the terminal velocity is, it's the steady state speed reached by an object in free fall. As v increases and the drag on the object increases, eventually the drag force will equal the weight of the object. So the drag force on the object will equal the weight of the object. That will result in a neutral force balance on that object, so a zero acceleration state. At that point, the object has reached terminal velocity. How do we calculate terminal velocity? Well, as we mentioned before, it's simply when the acceleration of the object is zero, when it has a neutral force balance after it's been in flight for some time. So essentially we could say kv squared minus mg is equal to ma is equal to 0, because a is going to be equal to 0 when the object has reached terminal velocity or steady state speed. So we're just going to use a subscript t here to remind us that this equation only applies for the terminal velocity. So kv t squared minus mg is equal to 0. We can now do the algebra to solve for the terminal velocity, which yields this equation right here. This equation is not deceptively simple. It really is just the square root of the weight of the object over the overall drag characteristic of the object in the medium through which it moves, k, which was a given at the beginning of the problem. So again, remember k is not just a function of the shape of the object, but also a function of the density of the medium through which the object moves. This 0.0002 Newton second squared per meter squared will change as the shape of the object changes and the medium changes. So, given the values that were granted at the beginning of the problem, the mass is 350 grams, the magnitude of gravitational acceleration on the moon is approximately 1.625 meters per second squared, and the overall drag characteristic of the object and the medium is 0.0002 Newton second squared per meter squared. We plug that into the above equation right here, and we get a terminal velocity of 53.3268 meters per second. So this is essentially the maximum theoretical speed we can expect. Now we go back to the v equals v of y function that we derived. And we plug in the same knowns from the previous page, except now what we want to say is, or what we want to determine is, what is the velocity of the object as it hits the ground? Well, the ground is y equals 0. We started at h equals 400 meters. So we have y equals 0, h is 400 meters, and then we have the same knowns and givens as were on the previous page. If we plug all these values into our calculator, we'll see that the velocity at y equals 0, or the velocity when the object hits the ground, because remember we defined the ground as y equals 0, the velocity at y equals 0 is 32.302 meters per second. So two great things about that result. One, it's less than the terminal velocity, so we know that it was a valid result out of this function right here, so we can trust it and we can use it. Because remember, we can't use any values that are greater than the terminal velocity, but we can use all the values that are less than the terminal velocity. We compare this 32.302 meters per second that the object is traveling at when it hits the ground to the terminal velocity, or the maximum theoretical speed, being 53.3268 meters per second. We'll see that when the object hits the ground, it's traveling at approximately 60.57% of its maximum theoretical speed, which means the object has quite a bit more room to grow in terms of speed, and it hit the ground relatively prematurely, and it could have picked up quite a bit more velocity if it had more h to travel. Okay, so that's it for this video. I really appreciate you watching. Thank you, and I'll see you next time.